there are really three ways to approach mechanics problems. One is forces and kinematics. That's what we did in the beginning of the class. That's where you're thinking about your position as a function of time, and you're looking at detailed motion. The forces tell you the accelerations, etc. A second way is with energy. That's what we've been working on recently. And here, energy, you have different types, so it's kind of hard to keep up with, kind of a zoo of types of energy. The key is that it is conserved. Energy is conserved for an isolated system or for the universe. And this is good for solving problems where you have sort of initial state, final state situations. Not necessarily the details of the motion during every second, like for forces and kinematics. The third one is the topic of this part of the class. The third one is momentum. That is our new topic, momentum. One advantage, there's only one type. Well, for now. In this class, there's only one type. It's conserved, so we're going to use conservation rules just like with energy. That's good. And it's kind of good for collisions and interactions. Collisions and interactions. Now, to be clear, you could solve any mechanics problem with any one of these three methods, or some combination of these three methods. It's just different methods are sort of lend themselves to different kinds of problems: detailed motion, initial, final, collisions and interactions. So you'll see that as we go. Now, one thing about momentum I want to point out is that it is conserved, but let's get a little more specific, as a vector, because momentum, p, so little p is momentum, it's the vector mass times velocity. So it's sort of a quantity of motion, as Newton would say. Mass times velocity, p equals mv. It is in kilogram meters per second. And that unit has no name. So if you do something really fundamental discovery about momentum, maybe they'll name it after you, because right now it is not named after anyone. Hard to believe. And one thing to keep in mind, it's conserved as a vector. So what that means is that p final minus p initial equals 0. And you'll see why, as we go, why the vector part is important. One reason it's important is it gives you conservation in all three dimensions. It means that px final must equal px initial, and py final equals py initial, and pz final equals pz initial. So that's useful for problems. It gives you three equations. But also there's other sort of more fundamental reasons why it's interesting that it's conserved as a vector while energy is conserved as a scalar, which we'll get to. Let's look at the relationship between momentum and Newton's laws. So open your Principias to page XVII, and let's first look at Newton's first law. An object in motion remains in motion. Here's an object. It has velocity v, it's in motion. Or an object at rest remains at rest. So if you think, well, this has velocity, also has momentum. So it's retaining its momentum. Here, this has no momentum. It's retaining a state of no momentum. So what this one is really saying in terms of momentum is that momentum is constant. He didn't say the part about the isolated system, but it's basically implied. So momentum is constant or conserved. So the first one is really just saying conservation of momentum. Let's look at Newton's second law. So Newton's second law is basically if you have a mass here and you apply a force to it, it accelerates. We know it as F equals ma, right? F equals ma. Well, if it's accelerating, it's increasing its velocity. And if it's increasing its velocity, it's increasing its momentum. So let's write this that way. Let's see, we could write it as m dv dt. And if we're always working where the mass is constant, which we usually are, we're usually applying Newton's laws to just point particles or finite particles that don't change mass, then we could put the mass inside the derivative. It's just a constant, it can go in there. So that's equal to dmv dt. Oh, what is mv? It's p. Oh, dp dt. So Newton's second law really isn't F equals ma. It's that the force equals the time rate of change of the momentum. So you can write that in terms of momentum as well. Interesting. Let's look at Newton's third law. Let's see, yeah, so Newton's third law, for every action, there's an equal and opposite reaction. So for this one, let's draw a couple of masses interacting with each other. So here we have M1, and here we have M2, right? And I don't know, let's say they're going to feel a force on each other. It could be a gravitational force that's attractive. It could be an electrostatic force that's repulsive. Doesn't really matter. Let's make it repulsive. So let's say this would be the force F12, the force that 1 applies to 2. Well, according to Newton's third law, there'd have to also be, this one would have to feel an equal and opposite force that we would probably label F21, the force that 2 applies to 1. It could be electrostatic, it could be gravitational, it could be that they touch, it could be a contact force. Any interaction between these two, the two forces have to balance, right? So what does that mean? Well, we could also say this one has momentum, P1, and this one has momentum, P2, right? And if they're going to feel these forces, then this one is going to have a momentum, a change of momentum, dp2 dt2. dp2 dt, or dp2 dt, and this one is going to have a change of momentum, dp1 dt. Okay? These are all vector quantities. The forces are vectors, the momentum's vector, the rate of change of momentum is a vector. So we know that the change of momentum here is equal to this force. The change of momentum here is equal to that force, right? Well, then what this means, if we add these two vectors and they have to be 0, we could add these two vectors and they have to be 0. dp1 dt plus dp2 dt equals 0, because the sum of the two forces is equal to 0. The sum of the two momenta is equal to 0. If that's equal to 0, what is the momentum of this one plus the momentum of that one? It's the momentum of the whole system. Right? This must also be equal to dp total dt. The system only has those two particles, and that is its total momentum, p1 plus p2. So what it's saying is, for this isolated system, the momentum is constant. Momentum is constant. Or you could say the momentum is conserved. So this one is just a statement of conservation of momentum, kind of just like that one is. Number 3 and number 1 are both conservation of momentum. So they're still Newton's laws, and it's kind of like what we said earlier, that you can solve problems with forces in kinematics, or you can solve problems with momentum. Some things lend themselves to forces in kinematics, some things lend themselves to momentum. And you can write these laws in terms of kinematics or momentum. It's really the same information. I just wanted you to see that you can sort of think of it that way. Newton wasn't real specific. He said this, the state of motion. Maybe he meant momentum, who knows? Now I'm going to demonstrate conservation of momentum, but you need two bodies to demonstrate that. So I'm going to bring in undergraduate Sina.
Hello, world.
Okay, so Sina should be studying English Lit or some lesser subject right now, but I asked him, he agreed to come do this demo with me.
I was actually bullied into doing this, for the record.
No, this is total voluntary. So what we're going to do is we're going to be on our little carts here, and Sina will be here, all happy undergraduate, and I will be here. I've seen some stuff, I've been through it. So neither one of us are going to be moving, 0 velocity, so our momentum is 0. My momentum is 0, his momentum is 0, the total momentum is 0. Then we're going to push off of each other and see what happens. All right, so let's line these up here like this. Let's get back on yours. And 3, 2, 1. All right. So after we pushed, we both started moving. Right? We got a velocity. So Sina is going this way with what we'll call V Cena, and I am going this way with what we'll call VJ, V for Jason. Now, it looks like we've created momentum. It looks like we forgot to conserve momentum. How do we explain this, Cena?
Well, momentum actually adds like a vector, as you see by the arrows on top of the labels.
Right.
So it doesn't add like a scalar.
So MV Jason plus MV Cena must be 0. But right, since they're opposite directions, if you did it in 1D, you would think of 1 as negative. You could say minus M, the magnitude of my velocity, if you call me the negative direction, plus the magnitude of Cena's velocity, if you call him the positive direction, would be equal to 0. Right? Yes, it's because momentum adds as a vector, right? What did I do? Oh, I left off my notation, exactly. And Cena needs that because he's about to tell us, calculate for us. It looked like we went about the same speed, but should we go the same speed? What speed should we both be going here?
Well, let's see how much freshman physics I remember.
Yeah.
So move this to the other side. We have mass of Jason.
Right, that's Cena. So you should have been going how fast? Solve for you. Cena. Right. Ah. So his velocity should have been a factor of the ratio of our masses more than my velocity. So now we got to get a little bit personal. The ratio of our masses. I don't know if we want to get into this here. Whisper, how much do you weigh right now? Yeah, okay, I'm a little more. So this factor here is about 1.15. So we would say that my velocity with a cursive J, they don't teach cursive anymore, would be his velocity would be 1.15 times my velocity, like that. So that's not a huge noticeable difference. You know, if you watch closely, you might be able to tell that he was recoiling faster than I was. So what I'm going to do is I'm going to gain 30 pounds real quick. Now, one way would be, where should we go eat real quick?
Whataburger?
Okay, camera guy can stay. We'll go to Whataburger. No, let's not do that. What I'll do is I'll throw on 30 kilos of weight onto my cart. So let's reset up Whataburger. And now with an extra 30 kilos, that ratio should go up quite a bit. And hopefully you'll be able to see that Cena does indeed move quite a bit faster. I'm also going to push him really hard, so that will also help. Let's see. All right. No, I can't get sideways. Here we go. Let's reline it up. 3, 2, 1. There you go. He went much faster than I did. Now we're going to illustrate the laws of conservation of momentum with a watermelon. Why do we drop watermelons from Rice Stadium? Not because it's easy, but because it's hard. Well, that was fun. Now we got to talk about the physics and the momentum of the watermelon drop. That's weird. I mean, there's no seeds in this watermelon, and I know they can make them grow without seeds. They make them sterile somehow. But this one has dents where the seeds used to be, right? So there's where the seeds were, but there's no seeds. I just smashed it open myself. It was closed a minute ago. So how do they get the seeds out? Maybe a chemical that I'm eating? I don't know. I'm going to not think about that, about what chemicals are doing to my body right now, because I swear I opened the watermelon myself when I dropped. Okay, anyway, let's not worry about it. There's no seeds somehow. So let's look at our watermelon drop. And let's see. So we had it coming down, and it fell from on high like that, smashed into the ground. And let's set up a coordinate system here. So we're going to have plus x that way, plus z that way. So, y must be into the board. Like that. There's our coordinate system, and we know what happened. It came down, and it smashed and made a mess on the ground. What does that have to do with momentum? Well, let's see. So first, let's think about the xy momentum. All right, let's look down. Okay, so we're going to look down this way. So we could write xy kind of like this. So now here's x, and there's y. And what do we see if we watch this thing going down? Well, you looked down. You saw the footage of the thing going down. It's a watermelon, and it's falling. And it has no velocity in the x, and it has no velocity in the y. Therefore, it has no momentum in the x. Px equals 0, Py equals 0. All right? That's the initial values, Pxi, Pxy equals 0. And then hit the ground and it smashed. Right? Suddenly stuff goes everywhere. There's this explosion. We're showing it to you now, and stuff flew around, chunks flew off in all kinds of directions like that. Boom, on the ground. Right? So clearly, pieces of the watermelon have picked up momentum in x and y. But to conserve momentum, it has to remain 0. The vector sum of all the momentum vectors has to remain 0, because we have to conserve momentum in x and we have to conserve momentum in y. This is why when it explodes, it makes a perfectly round little circle. If you look at the edges of this, we'll show it to you again. It's a perfect circle. And as you watch the things fly away, you can see big chunks are always flying away in opposite directions. I found one class where the professor actually made them analyze the video and estimate the masses of the chunks and make sure it really does come out to be 0. Right? So here, Px final, it's still 0, right? Because momentum conserves as a vector. Py final, it's still 0. This is actually related to how they discover new particles at the Large Hadron Collider and other high energy physics experiments, is they look for missing mass. They look for missing momentum. So they know how much momentum went in, they watch the big explosion, they detect all the particles that they know about, and it should conserve momentum. And if it doesn't, that means there must be particles that either they don't know about or their detector doesn't detect. So this idea is very similar to how they discover things like Higgs's and tops and all that stuff. So that's xy, some momentum information there. What about z? This is where it kind of looks like we violated conservation of momentum, right? Because the thing stopped, right? So we look into z, the watermelon was falling, it was speeding up, had a big value of pz, and that value of pz was changing in time, actually, right? So there was a force in the z due to gravity, dpz dt, getting bigger, bigger, bigger. It was very big until it hit the surface of the Earth and then splat, and then pz equals 0. So there's two ways to think about this. One is it's not an isolated system anymore. Right? So we had an isolated system of the watermelon, but it had an external force applied to it that increased pz, and then when it hit the ground, it had a big external force the other way that took that pz, decreased it back to 0. So if you want to think of the watermelon as the isolated system, it wasn't isolated. It had forces applied. You could also do it this way, though. You could think of the Earth and the watermelon together. That's not a very accurate view of the Earth. But if we bring the Earth in, and we say it's the watermelon Earth system, we could ask ourselves, what's the momentum of the watermelon Earth system? Well, if later we'll talk about gravitation, and we'll see that the watermelon feels a gravitational force due to the Earth, but according to Newton's third law, and according to gravitation, the Earth feels the same force due to the watermelon. And if you calculate the watermelon's acceleration at that height, it's about 9.8 meters per second squared. If you calculate the Earth's acceleration, it's about 9.8 times 10 to the minus 4 meters per second squared. Right? The Earth is so massive, you don't really notice the Earth accelerating towards the watermelon, but it does. So as they accelerate towards each other, the total momentum is 0. This has a momentum growing this way, This has a momentum going this way. They add as vectors, and the momentum is 0. And then they smash into each other. They both stop accelerating. Their velocities go to 0, and the final momentum is also 0. So either way you think about it, you can justify this in x, y, and z in terms of momentum.